Okay, we're gonna get started. Everybody, hi. So I'd like to start by acknowledging and celebrating the first Australians on whose traditional lands we meet, pay our respect to elders past and present. And today, it's my pleasure to welcome Dr. Sanaa Hobeichi, who's a senior research associate at the AR Centre of Excellence for Weather of the 21st Century, and she's based at the Climate Change Research Centre at UNSW. Her research develops and applies artificial intelligence and machine learning methodologies to advance, climate research, with a focus on climate downscaling and climate extremes. She co-chairs the Access NRI Community Working Group on Machine Learning for Climate and Weather and leads initiatives that foster collaboration between climate science and the machine learning communities. And I'm really excited that she's here today and she's going to talk about enhancing drought prediction through machine learning. So take it away.
Thank you. Thanks everyone for coming. Thank you, Nicola, for inviting me. And it's really my pleasure to be presenting here at the RSES School Seminar Series. So in this talk, I'm going to focus on drought, and I'll show how we use observed drought impacts to improve our ability to predict droughts, where and when they're likely to happen. And a focus of this study is on the machine learning aspect, which if you haven't used it before, if you haven't used the method that I'm going to show, I really encourage you to give it a try. So first, I'm going to share some climate facts from the countries where I studied. You can see that those two little small countries in the Middle East, and that's where I studied. So in Lebanon, I did a bachelor in mathematics and computer science. Then I moved to Qatar. So both Lebanon and Qatar are my home country. In Qatar, I did a master's in environmental and biological science, and my focus was on remote sensing. Then I moved to Australia, where I did a PhD in climate science at UNSW, Sydney. So climate facts. Lebanon is the only country in the Middle East that does not have a desert. So you can imagine a snowy mountain in winter and no rain for 3 months during summer, where people can enjoy some sunny beach. Now, Qatar is completely the opposite. It's one of the driest countries on planet. Rain falls approximately only 8 days per year. And when it rains a lot. It receives 80 millimeter every year, but all concentrated over 8 days. And so when I was in Qatar, I was a math teacher. And usually on rainy days, students don't come to school. They stay at home to enjoy the rain in their backyards. And also another fact that if you haven't heard about this vegetable, there is something called desert truffles. And these only grow underground after substantial rainfall. So we don't see them every year, only every few years. And they're served as luxury dishes. Now, I tried only one bite of this, and that's how it looks. And it tastes like potato, but with lots of grain sound that you can feel. And another fact is that during summer, so from June to September in Qatar, daytime temperature often exceed 45 Celsius degrees every day. All right, now my research. Nicola introduced me really well. So my research is really about developing machine learning methods and statistical frameworks across a range of Earth science applications. And this includes data fusion techniques with statistical approaches focused on water, energy, and carbon cycles, climate downscaling, and benchmarking of machine learning models. I also looked at quantifying and enhancing the predictability of extreme and compound weather events. Also do some work on renewable energy and environmental, a bit of urban environmental modeling. Now let's start the actual topic of this presentation, drought. So drought is one of the most complex natural hazards. And it usually starts with a period of low rainfall of a month or longer that causes water shortages, and this water shortage cascades through the ecosystem, agriculture, and communities, and it can lead to lots of impacts. For example, it can threaten water and food security, but also slow down economic growth. It can cause long-lasting environmental damages. It can affect human health and well-being. And also, droughts are very interconnected with other extremes, like, for example, heat waves due to higher temperatures and to forest fires due to vegetation drying. So, droughts can actually manifest in different forms. This depends on where the lack of water is observed and the impacts that result. And this diagram illustrates all these forms. We start on the top with the natural variability, which is characterized by shifts in large-scale atmospheric and oceanic patterns, and these can lead to precipitation deficit or high potential evapotranspiration. And this is the early sign of what we call meteorological drought. So we typically see a period of time over a region where we have less than usual rainfall, or we can see that the atmosphere is demanding more moisture than the land can supply. And this leads to reduced runoff, infiltration, and groundwater recharge. Then this also leads to soil moisture deficit. And when there is no much water in the soil, plants cannot access the moisture and the water that they need, and we start seeing vegetation and crops failing. And that's the type of drought that farmers experience, which we call agricultural drought or soil moisture drought. And as the water shortage continues, it starts hitting our hydrological system, and we see reduced stream flow and inflow to reservoirs, lakes, and wetlands, and lower groundwater table. And that's what we call hydrological drought that affects the water supply system. And all these physical changes lead to economic, social, and environmental impacts. So, for example, with the economic impact, we start seeing a reduction in the agricultural yield. And with social impact, we start seeing some restriction on water usage or some displacement because of lack of water. And we also start seeing environmental damages. So also human activities humans are not only impacted by drought, but they also can amplify droughts. For example, by water extraction, they lead to a reduction in groundwater recharge, and also by urbanization and land use change, that leads to increase in evapotranspiration, which eventually amplify the drought. So overall, drought is not a single event or form, and it's rather a chain of linked processes that starts with atmospheric anomalies and then moves through the landscape to society. In Australia, droughts are very frequent. Actually, Australia is one of the most drought-prone continents in the world because of the very highly variable climate. And we saw in the previous diagram, it all starts with natural variability. And Australia ranks 5th globally for economic damage from drought. For example, the 2017-2019 Tinderbox Drought, which affected Eastern Australia and led to the Black Summer bushfires, the total loss estimated from this event was $63 billion, $53 billion caused by the drought, and $10 billion from fires. And there are two major challenges here. First, there's increasing uncertainty around how climate change will shape drought in the future. And that was highlighted in the National Climate Risk Assessment recently. And also, we have limited capacity to provide accurate seasonal and subseasonal drought forecasts. If drought events can be forecasted in a reliable way several months ahead, this would help guide decisions and reduce losses. And from here, I'm going to focus on this particular challenge. How can we improve our capacity to forecast droughts? Typically, to forecast subseasonal or seasonal drought, a top-down approach is adopted. And it starts with subseasonal to seasonal prediction of key climate variables that are linked to droughts. So we saw in the previous slide, in the diagram, there are so many variables that are linked to drought. So we start forecasting those. And then we calculate a drought index. So, sorry, I forgot to mention, we already have operational seasonal forecasting capabilities with RSES, which provides weekly to seasonal forecasts. Now we take a variable of interest and we calculate a drought index. A drought index is like an anomaly or a Z-score in a climate variable or many climate variables. And then we set a threshold, and based on that threshold, we forecast drought conditions. Now, one question arises is which type of water deficit should we capture? So which drought index should we pick? And which means which type of water deficit should we capture? Is it rainfall, soil moisture anomaly, runoff anomaly, what exactly? And to answer this, it really depends on who needs this information. Are farmers interested, or water resource managers, or who exactly? But basically, we know that everyone needs this information. And that's actually highlights the limitation of traditional drought indices. First, they do not uncover all forms of drought, and that's because they only analyze a narrow selection of climate variables. But we know that drought results from complex interaction between multiple climate variables. And also another limitation is that they're subjective. So the drought conditions are very sensitive to the threshold that is used. And also these indices are typically not validated. So we don't really know how well the drought indices reflect on the ground realities. So how can we do better? We could develop a drought framework that can first identify droughts that lead to impacts that matter to people in any form, whether it's meteorological, agriculture, or anything. And we built a framework that can inject multiple causing mechanisms and contributing factors to droughts. And also we want that framework to reflect on the ground reality, actual droughts that happened. So we developed a method that can do this. And in this method, unlike the previous approach, we start with real droughts that were felt and had impacts. So we looked at reported drought impacts, and then we looked at the coinciding climate when this drought happened. Next, we built a damage function using machine learning that can map the climate conditions to drought. And finally, once we have this damage function, we can use it to predict impactful droughts. Now, we can add some forecasting capabilities to this approach by linking the droughts to climate from the previous month. And this way, we can use the damage function to forecast droughts. Now, I'm going to go step by step, like explain each of these steps in more details. We found reported drought impacts in reports from industry, government, news, and many other resources. And these reported drought impacts, for example, they look like this: crops being grazed or cut for hay and silage, or water supplies in most major population centers have been affected, or some impacts talking about water level in storage dam, or for example, saying that soil moisture levels were not good enough for late planting, and really so many other drought impacts that were reported and we found in the different sources. And we compiled a drought impact database for Texas, and also for Southeast Australia. And yeah, there are so many, like, I think we looked at more than few hundreds reports, and we extracted the drought impact information. So for the example of Southeast Australia, those black pods are the locations where we found drought impacts. And we prepared our database in an Excel sheet where we showed the location, the observed impact, the time, and we added a label, drought label, which says one means there is drought, 0 means there is no drought. So in order to build a model that understands what's a drought, we need also to show it examples of no drought. And our database included nearly 1,000 monthly records that cover both drought and no drought conditions. Next, we identified the prevailing climate conditions during those drought and no drought events, and that's how we expanded our database. So we included, during those drought events, some local climate conditions like related to precipitation, evapotranspiration, runoff, really lots of variables that are linked to droughts. And we also included large-scale climate drivers that are known to impact weather and droughts in Australia. In particular, we included ENSO, which is a periodic ocean atmosphere pattern in the tropical Pacific, and that alternates between a warm phase El Nino and a cold phase La Nina. We also included information about SAM, which is a climate mode that describes the north-south shift of the westerly wind belt around Antarctica, also known to impact climate weather in Australia. And finally, we included also IOD, which is a fluctuation in sea surface temperature between the Western and Eastern Indian Ocean. And this way, we had a database that is ready for building a machine learning model that is damage function. So we wanted to fit a model such that it takes the large climate drivers and the local climate conditions as input, and it can predict drought probability. So this input, we call it climate predictors or features. And we're trying to predict drought probability. So to train the model, we'll just let it see the labels or the target variable, which is drought, which is binary here. And we picked random forest for many reasons. Like random forest is very easy, like it's a very easy to implement. We don't need, unlike the other machine learning methods, we don't need to worry about architectures or how to choose the right parameters. So we built it as a drought indicator, and we wanted to use it to model the complex relationships between climate variable and drought occurrence. So random forest is not linear, so it can capture well the complex relationships. And also it can operate without requiring prior assumptions about the mathematical form or climate drought relationships. And this is particularly why we did not use a statistical method. So because we don't really know the form of the mathematical formula that can link those variables. And we use it to estimate the conditional probability of drought, giving the specific climate inputs. Now, I'll show a few technical slides just to show you how random forest operates and what it is. So it's a collection of decision trees where each tree is trained independently on a different subset of the data. So we have a training data, but every tree will see a different subset, and all the trees train in parallel. They don't see each other, which means that they're sort of independent, but also the algorithm is very fast. And it can perform regression and classification tasks. In our case, we use it to perform classification tasks because the target variable was 1 or 0. And we're predicting the probability of probability of drought. And each tree outputs only a single prediction. separate from all the other trees, and then we average predictions from all the trees to make the final prediction. And the idea is that we start with a root node, and this root node starts splitting into two children. Every node can split into two children. And the goal of each split is to make children nodes as pure as possible. For example, in this example, you see in the root node, the zeros and the ones, these are our labels. Now, basically in our database, we had 1,000 records, but just for simplicity, I'm showing like 12 samples. They're a mix of one drought and no drought. And the idea is that the algorithm needs to find a feature or predictor, temperature, for example, and a threshold that splits the data, the zeros and ones, so that the nodes are purer than the parent. In a perfect case, we would like to see all the ones go for one child and all the zeros go in one child, but that doesn't happen. So there is a metric of impurity, multiple metrics of impurity. One of them is called the Gini index, and that's the formula. So basically, we go to the parent, we calculate the probability of zeros, probability of one, and then we apply this formula, we get an impurity value, in this case 0.5. Then we do the same thing for each child. And after we find the Gini of the two children, we do a weighted average, taking into consideration the number of samples in each case, and then we get a new value. So the old Gini value was 0.5, the new value is 0.43, which means that the impurity was reduced, and so we have a gain. And the algorithm at each node tests all possible features and thresholds and chooses the split that gives the greatest reduction in impurity or the greatest gain. And splitting continues until certain stopping criteria are met. Could be because now the tree is too deep, or we don't have many samples in the leaf nodes, or it could be because we cannot improve the impurity. Now, once we have a trained random forest or tree in this case, we can use it to make predictions. So for example, in that case, if we're asking what is the probability of drought, if temperature is 15, so we're here, that's the path for temperature is 15, and rainfall is 2 millimeter. So we're taking this path. In that case, this leaf node gives us the probability of drought, probability of 1 is 2/3. And what I'm showing you here just happens for all the trees. Okay, this is the end of my technical part. Now, if you'd like to really see an example of how to use random forest, how to evaluate it, that's a tutorial that I've developed with colleagues. If you'd like I can share the slides and you can see the link. So we trained our random forest. We can now use the random forest to make actual predictions. And in this case, we use random forest to predict maps that show us the probability of droughts during the Tinderbox drought. So we've got here maps from January 2017 to end of 2020. And dark red means there's high probability of drought. Dark blue, there's no probability of drought. And yeah, we focus on this region that was impacted by the drought. And these maps gave us insight on drought development and evolution, both spatially and temporally during the Tinderbox drought. So we found that climate conditions during the winters of 2017, 2018, and 2019 indicated a high probability of drought, and they were like the precursor of drought. And also we found that the probability of drought was very high during July, August 2019, October 2019 to February 2020. And this coincided with the bushfires. We also applied a feature importance analysis to identify which variables provide the most useful information for drought prediction. Random Forest does this analysis natively, and when a feature that is known to drive drought is ranked highly, then we can fairly say that it's a dominant driver of drought. So when we did this analysis by looking at all Australian droughts and we start ranking the different drivers, we found that ENSO and SAM, so in particular ENSO, is a very important driver of drought. So we could say that Australian droughts are sensitive to large-scale climate drivers and ENSO in particular. But when we looked at the Tinderbox drought in particular, we found that actually the local factors played a larger role in determining drought predictability. But also this means that in general, including ENSO, SAM, and IOD in our drought framework improves our ability to predict drought, but these climate modes are typically absent from traditional drought indices. And this study was published yesterday. It was led by a student, Matthew Grant from UNSW. And it examines how time and area under drought have changed since the early 20th century. So if we took all the records from 1911 to 2020, we see that there is a decline in time and area under drought in Southeast Australia. However, we see that these patterns reverse and we see increasing trends in these drought metrics across most regions when we looked at the last 3 decades. Now, I've said that this approach is better than the drought indices, but I haven't really showed you the performance of Random Forest and the other drought indices. So in this example, we applied the same drought framework to predict droughts in Texas, just because it was very easy to find the drought reports and drought impacts. And those small dots are the locations where we found droughts, and they represent the different ecoregions in Texas. And the drought indices that we looked at were very commonly used. These include SPI. It's a function, it's like an anomaly in precipitation. PDSI is another one that is a function of precipitation and potential evapotranspiration. Eddy is a function of potential evapotranspiration, but USDM is actually the current state-of-the-art index of drought conditions in the US. And it's a function of the local climate variables, and also some of the climate indices, impact reports, and experts' opinion. So we were not trying to beat USDM because it's really state-of-the-art and it's not automated. Like people sit together and they look at different indices and make decisions. But if our method which is automated, can perform similarly to USDM, that's a win. Our approach was that we have our data, we split the data into training, and then we keep some 25% of the data for testing. But we also repeated this process of training, testing, and evaluating 100 times just to make sure that our results are robust and not sensitive to the randomization in Random Forest. So we looked at 3 metrics: accuracy, because our data was balanced, so we didn't need to use balanced accuracy. So accuracy measures how often the prediction matches the observation. And we use true positive, which looks at how many observed drought were correctly predicted as drought, but also true negative, which tells us how many observed no drought were correctly predicted as no drought. And we found that for accuracy, both Random Forest and USDM are the best. For true positive rate, Random Forest is doing well, so we've got more than 92% accuracy, but USDM is a bit better. And this SPI with a threshold of 0 was even better, also better, but we see that SPI was really good in true positive, but it wasn't good in true negative, which means that it just kept predicting drought, even when it wasn't a drought. So, and USDM was like slightly worse than random forest in the true negative. So basically, we could say that USDM and random forest were sort of performing the same. Now, we've also applied the same approach, but now to forecast the drought. And to do that, we just slightly change the database so that we align the climate with climate predictors with future drought. And when we built a model this way, it will be able to forecast drought. We tested 3 forecasting periods, 1 month F1, 2 month, and 3 month lead. And the summary here is that the framework has forecasting capability, but it declines compared to predictions of the concurrent drought conditions, which is expected. Now, currently, we are building a drought database for Australia. And we've also we extracted drought records from text sources and lots of reports. But this time it's a geospatial database. So you see, instead of like having point data, we have polygons that show the area that were impacted by drought. And this includes South Australia, Victoria, New South Wales, and Queensland. So to summarize, here we combined observed drought impacts, high-resolution climate data, and machine learning to build predictive and forecasting models for drought probabilities that can be also applied to any other hazard. And this framework allowed us to create a drought metric that uncovers all forms of drought and is relevant to diverse users who need this information. It can forecast drought probability up to 3 months ahead, and it can identify historical drought events and trends in time under drought. Also, we use the explainability, explainable AI or feature importance analysis to identify drivers of drought. And currently, we're building a drought database for Australia to really expand this study. And random forest with the feature importance framework can be applied to other earth science applications. It's really powerful, and it really it also works with a small sample of data, like fewer samples than what usually machine learning models require. And I would really like to acknowledge all my collaborators, and this includes Kiara, who's here, Nerly, who was with you here, and really Georgie, she's here, and really many other people who like helped me understand droughts and supported this journey of drought and drought research. And this work was part of my postdoc at the Center of Excellence for Climate Extremes, CLEX, and currently at the 21st Century Weather. Yeah, that's all.
Great, thank you so much. We have time for questions.
Yeah, let's just go ahead. It's very interesting. Thank you so much, Sanaa. It was really good. You mentioned that the random forest can predict or forecast droughts with great precision or great accuracy. When you say that it predicts droughts, do you mean the last bit, the impacts, or does it also predict the components like soil moisture and precipitation and ground?
Yeah, that's a good question. So I'll go back to this diagram. Okay. So all the drought impacts come from here, right? And all this happen because things happen on the top. So we take variables starting from natural climate variability, like every box here, we take a relevant variable, And what we're trying to predict is are the droughts that lead to any of these.
So is there any way to add to that prediction lead time? So
Yes, yeah, exactly. That's what we did. So initially we were matching the variables, like to say, for example, variable January 2020 with drought January 2020. But if you match variables January 2020 with drought March 2020, then the model starts learning how to predict drought a couple of months ahead. That's how we built a separate model to be able to forecast like droughts 2 months ahead, 3 months ahead, 1 month ahead.
yeah, wow. So does that mean that you also found information about different drought durations?
So once you build a model and then you apply the model to generate lots of maps, you can start like do a separate analysis where you start looking at like duration of droughts, time out of under drought, area under drought. So all this analysis is based on the drought maps that were produced with this approach.
Another question on the prediction part. You showed good agreement with the USDA on your drought identification. How did your 0.85 level of prediction compare to other drought predictors?
You're talking about nearly there. No, yeah. Oh yeah, here actually. So compared to USDM, we're very similar overall when we looked at a bunch of metrics. So here I'm showing 3, actually in the paper we had 6. Now compared to, we're better than the other one. So that one based on evapotranspiration, precipitation, we're better than those. In some cases, that one was beating us, beating random forest, but just because it just kept saying drought. But yeah, overall,
That's not predicted.
that's not. That's oh, you mean the forecast? Yeah, same. No, sorry, not same. We did not do the analysis because these ones usually don't forecast.
Are there any forecast models that you can compare to?
So the other forecast model that we can compare to is the actual forecast that forecasts precipitation. And then we use that forecasted precipitation and we apply SPI on the forecasted precipitation. That's, if you want like to test it, that's how we can test it.
Maybe I can ask a question. Can you forecast drought better than other people?
Can we forecast droughts? Yes,
So
we
your model,
in forecasting drought. Yes, I'll tell you the reason. So currently, to forecast drought, people start by forecasting precipitation. But the capability of forecasting precipitation at the seasonal to subseasonal scale is not that good. So because they can't forecast precipitation really well, that's why drought would not be forecasted really well.
Thanks, Sanaa. Do you have like a sense of how the accuracy drops off with the lag time? And is 3 months as far as you could possibly go, or could you go further?
I did not try. Yeah.
Oh, okay,
Yeah, I did not try. I mean, it will drop, but yeah, I did not try.
so it holds up pretty well from 1 to 3 then. It's not like it's tearing off.
Yeah, so that was in Texas. Now, whether that would be the same thing in Australia, I don't know. Because Australia is super variable, like very, very variable. Like it's more tricky than in Texas.
I was interested in the analysis of the importance of the variables of supply. Does that change when you're looking at the nowcast versus the forecast? Does the importance of the feature importance change depending on whether you're forecasting or not?
Yeah, so we don't apply the variable importance. I did not apply it on the forecast. I did not try. So we mean which climate variable provides the most useful information to know something about future drought, that would be interesting. I haven't tried it.
I only have a question. What's the forecast for the next 3 months? We're coming to summer.
Yeah, we haven't. Yeah, we haven't tried it. Look, I really tend to not do forecasts in Australia just because it's very tricky. So that was just a proof of concept when we looked at the forecast, but I didn't have at all intention to do forecasting of droughts.
Sanaa, so the model that you develop basically is trying to predict or the occurrence of droughts, right? But what about the intensity of this extreme? Like, have you think about this?
Yeah, that's a good question. So basically, this is study I think that was published yesterday. Okay, so first you predict with random forest the probability of drought. If the probability of drought is above 0.5, then you'll say there is a drought. But if the probability is 0.9, then you will say there is an intense drought. So that's sort of the way you can look at intensity based on the magnitude, like the probability itself. And I think that's how this study, so that's a long study, but in part of it, they looked at the intensity from the probability itself.
Kiara was next.
I like how the audience is very like interactive. It's not usually I don't get so many questions.
So new question. Thinking about your flow diagram from meteorological conditions through the impact. If your drought impact articles of the flavor presumably reflected some of the economic and social impacts. And some of those impacts will be independent of what's going on in climate, or much less directly related to what's going on. Like might be the world reinforcement of these or something like this, which means that the conditions, the local conditions, create a disproportionately large impact on that. Is there a way? Do you see that as being an issue with this method? And is there a way to tease out non-climate related influences on that impact study?
Yeah, I mean, that's a good and difficult question. I'm going to try to answer. So the drought impacts came from climate statements, climate reports. Most of them are climate-based something. And someone or multiple people looked at these and looked at what was reported. And what was reported is really drought impact from weather. Not really it's not like the price, they were like the price of something was high because some economic or some inflation, or no, it was like there was failure in crops. We only the farmers could only produce 20% of the yield that they're used to. So it's really related to dry conditions and drought. So I would say that we try to use AI, a large language model that we try to train so that it can take these documents and find those statements and then figure out the location and the time, all of this, but we failed, we couldn't. So it was really verified by humans like us to make sure that we only include the record that makes sense.
Usually it's the other way around, no? The droughts precedes the economic shock.
Like a war somewhere maybe led to something else somewhere else. Looks like we'll leave early today.
I had some questions. Oh, yeah. Maybe I can ask the last question then, which is, I guess, when you come in from the climate science side and you look at machine learning, there's millions of tools and it's kind of hard to decide would you use a network or a random forest or something else? And I guess my question is, would you recommend using the random forest? And if you were to go back and start your initial study again, would you still take the same approach?
Yes, thank you. That was also a good question. So in the Texas study, which was the proof of concept, we tried many different algorithms, including random forest, another tree-based method called XGBoost. We tried multi-layer perceptron, which is a simple neural network, and also other ones. Now, my rule is that if your data is on a spreadsheet or can be loaded with a Panda data frame, start with random forest. It's the simplest and it always works well. Like if there is information in the data, it will be captured by random forest. And it doesn't need thousands of records. So always start with random forest. Now, if the data is image-based, then that's where you want to start to really struggle and figure out which architecture, which model, what you should use.
I think the recommendation for what we should do is a great way to finish. So if everybody can join me in thanking Sanaa again for a great talk. And I believe we have cake outside for anybody who wants to hang around.
Yeah, looking forward to it.
Excellent. Great talk.